Yeah, so I want to talk to you about the RISC-V IOMMU. This is a specification that we got ratified this year. So to start with, I want to thank everyone who collaborated and contributed on the IOMMU TG. It was an excellent collaborative development, and we got the specification ratified. So today I want to talk to you briefly about what an IOMMU does, why it's important, and what are some of the key capabilities that we built into the RISC-V IOMMU specification. So IOMMU is an I/O memory management unit. It's a system-level MMU, and it's used to connect DMA-capable I/O devices to system memory. And it's a very critical component. It's required for achieving a lot of functionality. I'll talk about the use cases where IOMMU is required. It's required to provide security against rogue DMAs and DMA-based attacks. And it is required for a number of safety-critical segments in order to achieve their objectives. So to summarize, in the RISC-V IOMMU specification, we took these requirements and we built a rich feature set that addresses a wide variety of segments all the way from embedded to servers. And we target two-stage address translation. I'll talk about why that's important. We support shared virtual addressing. We support PCI specifications around address translation services and page request interface. We support unmediated interrupt delivery to virtual machines, hardware performance monitors, and a bunch of other capabilities. So let's start with some of the use cases. So let's take an example of IOMMUs typically associated with a virtualization, but it is also useful for non-virtualized systems. So why is it useful in non-virtualized systems? Let's look at the picture on the left. If you, in case of a RISC-V heart, when software makes access to load or store from memory, the operating system can set up the memory management unit with a page table that can enforce the permissions on the memory that the software can access. Now, at the same time, if there was no IOMMU, then this software can program an I/O device to perform memory access, and those memory accesses will go through to system without any checks. So you don't get any protection from software bugs or malicious devices being plugged into your machine, and so on. With an IOMMU, now the operating system can enforce the same permission checks it enforces on the hard, on the I/O memory accesses as well. And it gives you the memory protection capability. It gives you, defense against software bugs that might be exploited or malicious devices. And in some cases, it gives you some functional benefits. For example, if you have some legacy device that can only DMA to low memory, you can use the IOMMU to redirect that address to high memory and get around the need for having things like bounce buffers. Second use case is when you're using virtualization. Now you've got many virtual machines, and your hypervisor is setting up a page table so that it can constrain each virtual machine to the memory that it is allowed to access. On the heart, there's two-stage page tables that are used, two-stage address translation, so that the operating system inside the VM can set up its own page tables, enforce its own address translation and protection policies, whereas the hypervisor can prevent one guest OS from accessing another guest OS memory or the hypervisor's memory itself. Right? Now, when you have to this kind of virtualized system, for maximal performance, you want the guest OS to master its own devices. So be able to directly program the devices without needing mediation through the hypervisor. But in the absence of an IOMMU, this direct device assignment is not possible, because then a guest VM could program the I/O devices to access memory of the hypervisor. It could program the device to access memory of the other VMs. And lack of an IOMMU requires the hypervisor to be the mediator, and that's a limiter for performance. Now, with the two-stage address translation in the IOMMU, the hypervisor can directly pass through the device control to the guest VM. The guest VM can use the first stage to enforce its permissions and policies and address translations as required. And in the G stage, the hypervisor can set up its memory access control policies. Let's look at a third use case, and this is an emerging use case. It's called shared virtual addressing. A lot of times you want accelerators to offload your work to an accelerator. For example, you might want to do, say, acceleration on a GPU or some kind of custom accelerator. And when you have these accelerators, you also want the ability to share pointers between the accelerator and the software that runs on the heart. Sharing pointers can be useful because now you can make the accelerator operate on rich data structures such as linked lists and trees. Without being able to share a pointer, you will have to marshal the data, package it up in an alternate format for the accelerator to work, and then when the accelerator is done its job, put it back in the format where the heart can work upon it. Now, this ability to share pointers unlocks this whole new use case where you can have fine-grained offload of work to the accelerators, and you could even do this offload directly from user space without needing to involve the supervisor. To do that, you need just like on the heart, you have the virtual addresses being translated by a heart MMU to a system physical address, enforcing the read-write permissions. You want the device to be able to access using the same virtual address, but then have the IOMMU enforce using the IDs provided by the device as to which address spaces it can access and translate that virtual address to a physical address so that both the heart and the accelerator can work on a common data structure. So this enables your low overhead invocation of accelerators. So how does the IOMMU do all of this? I talked about two-stage address translations, but unlike a heart MMU, which needs to deal with one page table at a time, the IOMMU has to deal with tens of devices or even hundreds of devices where each device might be associated with a different page table. And on a per transaction basis, it needs to select between the page table that it needs to use for the address translation and permission. So for that, we introduced this concept of a device ID, and in case of, and this is typically signaled along with the DMA. For example, in PCIe, there is the routing ID that is a 16-bit number that identifies the device. And we define a data structure called a device directory. So we can take the device ID that is signaled by the device, and the IOMMU will look up the device directory, and the device directory gives it a couple of pieces of information, one of them being the G-stage page table. Now, when you have got two-stage address translation in place, a second piece of ID is used. It's called the process ID, and your device context now points to a process directory. And now you take once you found the device context, you use the process ID, look into the process directory, and find a process context, which gives you the first stage or the VS stage page table. And now you can use the IOVA that was signaled by the device and do a two-stage address translation and find the physical address and enforce the permissions. So through this multi-level directory structures and page tables, the IOMMU is able to provide you isolation, protection, and also support the shared virtual addressing. You might be going, there's a lot of tables, and if every memory access needs to look up a device context, a process context, each of them are tri-tables and a page table, hey, that single transaction could turn into 20 memory accesses, right? Now you want to optimize for that, and what typically the IOMMUs do is they have address translation caches. So similar to TLBs, how TLBs help on the heart, they have address translation caches to cache contents from these directory structures and page tables. And the IOMMU defines the concept of an address translation cache. So when a transaction shows up, if you hit in that address translation cache, you don't need to walk any of the in-memory data structures. You can provide the translation and find the permissions from the cache. When you have a miss, you invoke a page walker in the IOMMU, which will go look up the directories and page tables and fill the address translation cache with the relevant information. Now, this leads to a question as to if I modify the table in memory, how do I make the IOMMU observe it? So we have to have some way to invalidate the cached contents and have the IOMMU observe the new content in memory. And that's where the IOMMU defines the concept of a command queue through which a IOMMU driver can queue commands to the IOMMU for address translation cache management. And this is an asynchronous, loosely coupled interface which allows software on multiple hearts to queue commands, and the IOMMU can then complete them. And that allows high performance interaction with the IOMMU. Sometimes you may, as part of your page table walk, as part of your directory structure walk, you might encounter faults. Those faults may be due to misprogramming, or it may be due to the device misbehaving, or it may be because there is some funny business going on. Somebody plugged in a rogue device, for example. Now, when the IOMMU encounters a fault, unlike the heart MMU where it can cause a trap and invoke a trap handler, the IOMMU has to work in an asynchronous manner. So the IOMMU defines a queue in memory called the fault or event queue. And when one of these faults or events occur, it queues a record into the fault queue, and the record contains information to identify the device, such as the device ID, the process ID, the virtual address that was used for the access, what type of fault was encountered. And the IOMMU then generates an interrupt to the IOMMU driver. The driver can then read the fault record and determine how to handle it. One thing to call out is, unlike CPU faults, like a page fault is recoverable because you can restart the instruction. In case of I/O, there's no concept of restarting the instruction. It's like an arrow that's left that's been fired. It's reached the IOMMU. IOMMU cannot hold on to it while software fixes it up. So I/O faults are usually not recoverable, which is also not nice. So how do we fix that? That's where PCIe came up with this concept of recoverable faults. So like I said, if once you fired the arrow, you can't take it back. But if you know that something's going to fault ahead of time, now you can recover from it. So for that, devices need to participate in this whole process. So with ATS, the devices have an address translation cache in the device. And it has a couple of benefits, one of them being able to recover from faults. And now the I/O flow turns into an initial step where the device, before making a memory access, requests an address translation from the IOMMU. And it can then cache that address translation in its device-side address translation cache. Now, this also has the benefit that a device knows its workload best. It knows what memory it's going to access next. And it allows the device to also prefetch address translations so that the overheads of translating an address can be overlapped with other I/O that may be ongoing. And also by having a dedicated address translation cache in the device versus the address translation cache in the IOMMU, which might be shared by multiple devices. Now you're not exposed to things like other devices thrashing your cached entries. You have your own cache that you can manage. So once you read an address translation, the IOMMU might tell the device that, hey, you asked for this translation, but it's not present because the OS has swapped it out, for example. Now, in response, the device can issue a page request. And when that page request message shows up, the IOMMU puts that into a queue called a page queue and notifies the IOMMU driver. IOMMU driver can invoke the memory management software. And once the page fault has been resolved, the driver will queue a page response into the command queue and say, IOMMU, please send a page response message back to the device. And when this page response message comes back to the device, it will retry its address translation request. Hopefully, it gets the translation now, and now it can make the memory access. So now, not only it gives you the performance benefits of having a dedicated address translation cache, being able to prefetch translations based on your access patterns, it also allows you to recover from page faults. Now, we saw how having the page tables allows you to directly pass through a device to a virtual machine, and through the use of the two-stage address translation, we are not exposed to any of the security issues. We still have to solve a problem, which is how do I get interrupts to that virtual machine? Because typically when a job is completed, the device either signals the completion or the occurrence of a fault through an interrupt. Now, if that interrupt needs to be mediated by the hypervisors, then you lose performance. So we want the ability by which you can deliver an interrupt directly to the virtual machine. And in order to support that, two specs have to come together. There's the advanced interrupt architecture and the IOMMU that were both ratified this year. What the advanced interrupt architecture defines is a interrupt controller called the incoming MSI collector, or IMSI. And in the IMSIC, there are dedicated interrupt register files for virtual supervisor level or guess. Now, in the IOMMU, we define the concept of an MSI page table, and we have a way to identify MSIs, which are normal memory writes, but they are to special memory regions. And when those MSI writes show up, the IOMMU uses the MSI page table to redirect that write to the heart's VS level interrupt file. And the VS level, once the interrupt is recorded in the interrupt file, the VS level interrupt file will then prioritize the interrupt and deliver it directly to the virtual machine, all without needing any hypervisor intervention. Now you might say, how many interrupt files can I build? The architecture allows you to build up to 64, but what if I need a 65th, right? So that's where a second facility comes into place. It's called memory resident interrupt file. So again, the architecture allows you to offload an hardware resident interrupt file to memory resident interrupt file. Typically, you do that if you are running, say, more virtual CPUs on a heart than the number of physical interrupt files that you have. It's typical overcommitting, where now in order to load a new virtual CPU, you have to offload from the hardware to memory. But you cannot predict when an interrupt shows up. So now, if a VS level interrupt file has been offloaded to memory and an interrupt shows up for that, the IOMMU, instead of setting the pending bit in the hardware interrupt file, will set a bit in this memory resident interrupt file using an operation similar to an atomic memory operation. It's an MOR. And it's not enough to just set a bit in memory. You have to tell the hypervisor that, hey, that virtual machine that you had descheduled and made memory resident has an interrupt pending, right? So it then generates an IOMMU initiated interrupt. It's called a notice interrupt, and that notice interrupt is directed to typically directed to the supervisor interrupt file in the IMSIC, and that tells the hypervisor that this memory resident interrupt file has some pending interrupts. So you may want to schedule that VM, load that MRIF back into the physical interrupt file, and have that interrupt delivered. So this capability allows you to oversubscribe the interrupt file. It also allows a simpler migration of VMs among hearts, so that when you're moving it from one heart to another, you offload the hardware interrupt file to memory. It can keep collecting interrupts in memory, and then once your migration is complete, load it back from memory into the hardware. Other things that the IOMMU can do, we defined a hardware performance monitor. It's a very useful tool for system integrators and for people trying to debug why they're not getting the performance that they expect. So the IOMMU supports a cycles counter. It supports up to 31 programmable event counters. We have support for things like counter inhibits, interrupts on counter overflows, so that you can sample them. You can filter counting by device ID or device ID ranges and process IDs. Right? So a very rich hardware performance monitoring capability built into the specification. Some systems might want to support little endian operation. Some systems might want to support big endian operation, big endian mode of memory, and some may want to support a mix. The RISC-V architecture allows for both, and likewise the IOMMU architecture supports little endian or big endian mode, and it's a dynamic configuration that you can choose if your system supports that. Likewise, you can build the IOMMU to support RV32. You can build it to support RV64. And if you support the concept of having, configurable XLAN, then the IOMMU supports having a mix of RV32 and RV64 guests all at the same time. It supports hardware updating of accessed and dirty bits in the page tables, which is a useful capability if you're trying to do VM migration and you want to know if memory is being dirtied by device accesses. Right? It supports a debug interface through which software can request address translations. For example, if you're a driver developer or you want to debug some bugs, you can use the debug interface to request the IOMMU to provide you a translation, and very conveniently, without having to worry about whether your page tables are set up right or your walk algorithm is right, and so on. And it supports customization. So there is enough fields left there, defined for custom extensions, so people can add custom extensions that they need. This picture shows how typically an IMMU would be integrated into the system. So you would have, IMMU is a look-aside device. It doesn't actually see the I/O data as it's flowing. So typically something like an I/O bridge would invoke the IMMU through a translation request interface where it can say, I received a DMA transaction, and here is its address, and it's trying to do a read or a write. Tell me the translated address and whether the access is allowed. And in response, the IMMU would do the address translation and provide access control checks and provide a response back to the bridge, which can then complete the I/O. But if there is an address translation cache miss, then the IMMU itself needs to walk data structures. And for that, there is a data structure interface through which the IMMU can insert memory reads and writes in order to walk tables. It has an interface by which the hard can access the memory mapped registers of the IMMU, and there's the ATS interface through which it can receive the page request messages and the ATS invalidation completions and so on. There's a couple of different ways the IMMU can be integrated into the system. One of them I call as a dedicated IMMU. This is, for example, if you had a high-performance graphics processing unit or high-performance accelerator, and you want to dedicate an IMMU just for that, you can build that. So you could have a dedicated IMMU which is built into or close to the accelerator device, and it handles translations just for that. You tune its ATC, its capacity for the needs of that accelerator. Sometimes you do not need that much performance out of that IMMU. You can share it among devices, in which case you can build an IMMU that is shared by multiple devices. Some of them may be connected through a root port, so they may be discrete plug-in devices. A third option is where you may have a centralized page table walker, but then you distribute the address translation caches. So in this example, I show this green ATC serving device A and B, the blue ATC serving device C and D. But if either of those ATCs have a miss, then they invoke this common page walk handler in order to refill the ATC with the updated translation. So multiple options are available for system integration, and the IMMU specification provides the maximal flexibility for all of these integration models. So to summarize, the IMMU specification that we ratified this year, it's a critical component to address functional, security, safety requirements across a wide variety of usages in the enterprise, cloud, HPC, across segments. And the RISC-V IOMMU technology, it unlocks new and exciting capabilities, such as being able to do device pass-through in a secure manner, with the IOMMU providing the address translation and protections, MSI redirections, shared virtual addressing, and support for PCIe address translation services and page request interfaces. Thank you.
So thank you, Ved. So we are kind of over, but we have time for one question, at least. Any question? One question. Go ahead.
In the slide, the PQ and the CQ slide, and what's the review, the TLB, the software view or the hardware page table walk?
Yes.
And the second question is the AND. AND is mandatory to use the hardware design, or we also could use a software fault to update the A and the D bit.
It is for hardware A and D updating.
This is the second question. The first question is the TLB review is software or hardware?
It is software. So the
software.
The protocol is because you have a page fault. The operating system needs to fix the page fault and then ask the device to retry its address translation request.
Okay.
So, Ved, thank you very much.
Thank you.